Well, welcome to video number 1 for Lesson A of Unit 5B. In this video, we're going to expand our understanding of energy to include what's called the electric potential energy and also introduce a new concept called the electric potential. By the end of this video, you should understand the difference between electric potential energy and electric potential. You should understand that the amount of electric potential energy that a charge has is equal to the work done to move the charge. You should be able to calculate the electric potential energy when given the magnitude of a test charge and the electric potential. This video it's mostly conceptually based and lays the groundwork for all the topics in future videos for this unit. So make sure your notes are ready and you stretch your video pausing and rewinding finger, and here we go. So we're going to begin by briefly reviewing the topic of conservation of energy, and you'll see why as we go along. Conservation of energy is a powerful tool for understanding the motion of mechanical systems. Basically, it says that when objects interact with one another, their total mechanical energy is conserved because of conservative forces. Two important conservative forces that we've studied are the force of gravity and the elastic force of a spring. In this picture here, we have a system consisting of the earth and a book. These two objects interact via the force of gravity so that if a force external to the system, which would be this hand, moves the book at a constant speed through a displacement, then the force does work on the system. This work represents a transfer of energy from the environment to the system. So the system's gravitational potential energy increases by the amount of work done. We say then that the work is equal to the change in energy. And we can pretty much say the same thing about springs. You know, when you compress a spring, you increase its potential energy. The work that you do compressing it is equal to the increase in that spring potential energy. So in both these cases, an external force is applied and work is done. This work represents a transfer of energy from the environment to the system. And in both cases, the increase in potential energy is equal to the amount of work done. In general, then, a system's potential energy is found by computing the work an external force must do to change that system's energy. Now, let's apply this idea to a system of charged particles. As in Unit 5A, we're going to talk here about source charges and test charges. These charges here are the source charges, meaning that they're fixed in place and they don't move, like they're stuck on a charged up balloon or something. The source charges exert an electric force on the charged particle Q, the test charge, in the hand. So the hand must exert an external force to move the charge at a constant speed from this point to this point, from point A to point B. This is just like lifting a book in a gravitational field, which results in increasing the book's gravitational potential energy. In this case, though, our hand is doing work on the charge here, which increases its electric potential energy, which we abbreviate UE. Therefore, the energy transfer shown in this picture then is equal to the work done is equal to the change in this electric potential energy. And we define electric potential energy as the energy that's stored in a system of charged particles due to their electrical interactions. Now, like gravitational potential energy, we pick a reference point from which to measure electric potential energy. We will set the electric potential energy as 0 at that point and then find the electric potential energy when the movable charge is at another position by finding the work done to move it there. Unlike gravitational potential energy, though, electric potential energy will increase or decrease relative to the type of charges that we're dealing with. For example, when we lift an object, we're moving it in the opposite direction of a gravitational field. So when we lower an object, we're moving it in the same direction as a gravitational field. So gravitational potential energy will increase when we move an object in the same direction as the field and decrease when we move it in the opposite direction of the field. This is because gravitational fields always point toward the center of the mass. With electric potential energy, though, the sign of the charges involved determine whether the energy is increased or decreased. When the charges are unlike, we have positive and negative charges, the electric potential energy increases when we move the charges away from each other, or decreases when we move the charges toward one another. Now, this is because unlike charges are attracted to each other, so it takes work to move them apart. Doing work on the system increases the potential energy. If the charges are the same, though, the electric potential energy increases when we move the charges closer to each other. This is because like charges are repelled, so it takes work to move them closer to each other. So as the two charges move closer together, the potential energy increases. Another way to think about this, is think about either of these two situations, which moving the charges toward or away from one another, which would require kind of effort, right? If the charges are unlike charges, they're already attracted to one another, so it would take effort to move them away from each other, and would take less effort to move them toward each other. So moving them closer together will decrease that electric potential energy, and moving them apart will increase that electric potential energy, and opposite when the charges are alike. So electric potential energy it's pretty easy to get our heads around. It's easy to compare it to gravitational potential energy. With gravitational potential energy, we're dealing with masses in a gravitational field, while with electric potential energy, we're dealing with charges in an electric field. Both concepts deal with how these fields affect the things within them. Also, both gravitational fields and electric fields arise because both masses and charges alter the space around them. However, while masses alter the space around them by setting up gravitational fields, charges not only alter the space around them by setting up electric fields, they also affect the space around them through something we call electric potential. So in order to talk about electric potential, we need to talk a little bit more about electric potential energy. To begin with, you need to understand that electric potential and electric potential energy are two different things. In Unit 5A, we introduced the concept of the electric field in order to understand forces between charges. In the field model, a source charge alters the space around it and sets up an electric field. That electric field is the agent that exerts a force on any other charge that enters it. And we found the force on a test charge with E equals F over Q, where Q was that test charge. Now we're going to try to understand electric potential energy in a similar way. Consider a group of source charges all fixed in place except for one that can move. We imagine that at every point in the space surrounding the fixed charges, there is some number that tells us how much potential energy the mobile charge would have if it were placed at that point. So using this figure here, let's imagine that our movable charge has a charge of 10 nanocoulomb, okay? And we choose point A down here as our 0 point for electric potential energy. So this is like the ground in a gravitational potential energy situation. Suppose that in order to move our happy little charge from point A to point B, we must do 3 microjoules of work. Well, because work equals a change in energy, we know that the electric potential energy of our charge then is going to be that 3 microjoules. Now, let's say we want to repeat this experiment, but instead of using a 10 nanocoulomb charge, we use a 20 nanocoulomb charge. We could repeat the entire thing, but we don't need to. We've doubled the amount of charge from 10 nanocoulombs to 20 nanocoulombs, so according to Coulomb's law, the electric force on this charged particle is also doubled, and because the work done is proportional to the force times the displacement, the work done to move the charge from A to B doubles as well to 6 microjoules. So our electric potential energy equals 6 microjoules here at point B. And if we were to double the charge again, the electric potential energy would double again. In general then, a charged particle's electric potential energy is proportional to its charge. Now, whenever two quantities are proportional to each other, their ratio is constant. In this example, the ratio of the charge's electric potential energy to the charge is constant. We can see this directly by calculating the ratio for the two different charges. So the ratio of potential energy to the charge for our first charge, 3 microcoulombs to 10 nanocoulombs, is 300 joules per coulomb. So what's happened here is this micro is 3 times 10 to the negative 6, nano is times 10 to the negative 9. So if you were to take 3 times 10 to the negative 6, divide it by 10 times 10 to the negative 9, you're going to get 300. Same thing if you take 6 microjoules to 20 nanocoulombs, you're going to get a ratio of 300 joules per coulomb. So using this constant ratio, we can write an expression for the electric potential energy that any charge would have at point B. And here is that expression, and we can use it to figure out how much potential energy any charge would have at point B. So this tells us then that there's a pretty special value, this 300 joules per coulomb, associated with point B. This value is special because it tells us how to find the electric potential energy of any charge that happens to be placed at point B. That is, it tells us the potential for making potential energy at point B. We call this value electric potential, and it's given the symbol V. So for our example here, at point B, the electric potential V is 300 joules per coulomb. Now that's specific to, that 300 joules per coulomb is specific to the example we looked at, but we can, this idea can be generalized. And we can say that any source charge will create an electric potential in the space around it. That is, any charge will alter the space around it so that we can calculate the potential for making potential energy at any point within that space. So at a point where the electric potential is V, the electric potential energy of a charged particle is UE equals Q times V, where V is that electric potential, and UE is electric potential energy, and Q in this case is the test charge placed within that vicinity around the source charge. Now from this we can see that the unit then of electric potential would be a joule per coulomb, and we give that a special meaning, special unit called a volt. Yes, it's true, we abbreviate electric potential with a V. It is measured in volts, the unit volts, with a V. So you have to be really careful when you're making sure that the V for electric potential and the V for volts are not the same V. And we've also got, of course, velocity, and later on when we start talking about fluids, we'll throw volume into things too. So it's going to be fun. Now it's also going to be important for you to recognize that the electric potential is not a property of the test charge, okay? It's a property of the source charge, and it depends only on their positions and charges, the positions and charges of the source charges. The electric potential of the source charges exists throughout space whether or not a test charge happens to be present. If a charged particle is brought to a point where the electric potential is some amount V, the charge's electric potential energy is given by this equation here. This is similar to an electric field, right? So an electric field exists around a charge regardless of whether another charge is placed within it or not, right? So in the same way, electric potential exists around a charge regardless of whether or not another charge is there to experience it. Electric potential, it's just another way to look at the alteration of space around a charge. Think about a battery. It has a certain voltage whether it's plugged into a device or not, right? Once it's plugged in and charges are allowed to move from one end to the other, we're kind of able to unlock that electric potential energy. So we can relate this to gravitational potential energy, all right? Another way to look at electric potential is to relate it to gravitational potential energy. Electric potential is like saying how much gravitational potential energy any mass would have at some point above the ground or some other reference point. Now, what would we need to do in order to say any mass would have so many joules of energy at point Y above the ground? Well, we would have to do the same thing we did here and look at the ratio of joules per kilogram for two masses. Now, just translate this idea into electric potential. It becomes electric potential is the amount of energy per charge any charged particle will have at point Y. Now, to distinguish electric potential from electric potential energy, we say that the electric potential is a property of the source charges. The electric potential is present whether or not a charged particle is there to experience it. Potential is measured in volts. Electric potential energy is the result of interactions between a charged particle with those source charges. And potential energy is measured in joules. So this concept of electric potential can be confusing when it's first encountered. Students will often confuse electric potential and electric potential energy. If you keep in mind, though, that electric potential is another way to describe the alteration of space around a charge and exists whether other charges are around or not, while electric potential energy depends on the interaction of charges, it should be easier to kind of get your mind around the two concepts. In the next video, we're going to look at ways in which we can visualize and use the electric potential. See you then.